It'll be in English, thanks to the gentleman on the first floor. Luckily, the slides are in English as well, so it won't be too much of a problem. So, hello everyone. It's nice to be again here. I was here on the first year when the conference actually started. It was in a really, really small room. I think there were like 20 of us. My presentation was in Croatian. Thank you. But anyway, today I hope it will be okay in English as well. So in case you don't know me, my name is Bojan Zdrnja. I work as a penetration tester in a Croatian company called Infigo. I'm quite involved with SENS. If you go to any of the SENS courses, or at least those two, 542, 504, you might get me as an instructor. Little hint, next year Budapest, if you want to go there and pay money to SENS, then that's fine with me, obviously. So the presentation today, since we are short on time, I'll be here exactly 30 minutes as I was originally supposed to. The presentation today will be about security of mobile applications. I held a similar presentation a couple of months ago, and this one actually has been extended to demonstrate different categories of vulnerabilities that we have identified in various mobile applications in maybe last 5 years. By nature, the majority of mobile applications that we actually tested are mobile banking applications. So I'll be talking mainly about internet banking applications here. So just for first question for everyone here, how many of you do have smartphones? The majority. How many of you do use mobile banking on your smartphones? Okay, and now, how many of you do use PIN codes on smartphones? This is a security company. I hope everyone will raise their hand. Okay, or you're too shy. This will be one of the main points that we actually verify when we are doing a penetration test on a mobile banking application. Obviously, besides server-side vulnerabilities, which can be particularly devastating, the biggest issue that we have with smartphones is what happens when you lose it, or what happens when someone steals the smartphone from you. Now, this is something that we have to protect against thoroughly, and this is something that we pay special attention to. As you can see here, this was done on approximately 30 mobile banking applications, so we covered pretty much a lot of the region here as well. Of course, the majority of banks are in Croatia, so this will kind of reflect on the status of mobile banking applications in Croatia. So first of all, just a little introduction. What's the problem here? Obviously, those devices are with us all the time. Those devices are turned on all the time. They keep connecting to different networks. Anyone connected to the wireless network here? Maybe? To the FSec? Yes? No? Okay, thank you very much, because I've been running man in the middle whole day and I captured your traffic. No, I'm just kidding. But this is one of the issues that we have with wireless networks, that we connect to absolutely everywhere. We connect to 3G, to 4G, whatever the next generation is, and those devices are constantly online. Obviously, the only thing that actually separates an attacker who steals the phone from us and our banking account is actually just a PIN code. 4 digits most of the time. Sometimes 6 if you're really lucky, but it'll be generally 4. Besides that, we can see that security tools on mobile devices are very, very limited. Even though we are on a security conference, I bet that I can count on one hand people who actually have antivirus installed on their mobile devices. If you have iPhones, no luck. You can't have it at all. If you have Android, maybe you do have some kind of antivirus, but unfortunately, those applications are still in very, very early phases, and they cannot even be compared to the antivirus applications that we have on our desktops. So let's take a look at several issues that we have with mobile devices, and typically we'll divide them into data at rest and data at transit to see exactly what we have to pay attention to. So today, those devices, when we access any application, be it mobile banking, be it Facebook, Twitter, whatever you want, those devices are used as authentication devices. Obviously, on Facebook, we will just use our username and password, and that's maybe not something that we care a lot about. But on mobile banking, we actually don't want to use a simple username and password. Why? Because if someone sees that, they can log in from another machine, right? From another mobile phone. We want something which will be very specific, which will be tied to the device that we have as much as possible, so the attacker cannot really replicate that easily. Now, we can see here that that device will be used as some kind of two-factor authentication. Obviously, the possession of the device is the first factor, the PIN code is the second factor. Similarly, as we have some kind of a token, like historically here in Croatia, most banks have tokens, this is very, very similar. And the programming background, the applications that we will have on our mobile phones, should actually work very, very similarly to those tokens, physical tokens that we have. So what happens here in the background actually? Like virtually all mobile banking applications that we tested so far, and this is a good thing, use some kind of OCRA or OAuth, open authentication algorithms to generate the codes which are used to authenticate you to the bank. Here we have two subcategories. One are time-based one-time password, the other one are counter-based one-time passwords. So typically banks today use time-based one-time passwords. What does it mean? This means that once you activate your application, you go to some kind of exchange, material exchange session with the bank, and once both sides know what they're talking about, the PIN is the only thing that protects the input into this algorithm. So when you open your favorite bank's mobile banking application, you enter the PIN, and the PIN is typically used to decrypt some kind of a secret, which is again used as input to this algorithm. For the time-based algorithm, we use the secret plus time, obviously, so it changes every minute or depending on what the interval is. For counter-based algorithms, we use the secret plus actually the sequential number of times that we authenticated to that service previously. Now these are typically generated, as I said, during the mobile banking application activation process. We will come back later to this. This is just like a basic thing that we need to store on the device. So obviously we just don't want that to be a PIN. Why? Remember what I said. We don't want someone to be able to log in to our application from another mobile device. If it's only a PIN and absolutely nothing else, we have a very similar thing as username and password authentication. With this, if I just go back one slide, with this we actually made our mobile device the second factor, something we need to possess, because that secret will be stored only on the mobile device. That secret is the input into this function plus the user's PIN, this way or another, and we have two factors. And this is something that we need to remember for later slides. The other thing we need to talk about here is protection of data in transit. So hopefully all the applications today will use some kind of SSL or TLS, don't take me for those words. I always say SSL, although we mean TLS here. Luckily, most of the vendors are actually pushing people towards that. So Apple will actually start mandating TLS version 1.2. If I'm not wrong, from 1st of January 2017, they will actually push TLS 1.2 as mandatory for absolutely everything. And you will have to actually deliberately turn off encryption, if it will be possible, just to make some kind of connection. With latest Android, Nougat, the nice thing here is that it does not trust user certificate authorities which are added to the mobile phone anymore. So if someone takes your mobile phone for 5 minutes, adds a malicious certificate authority in your mobile phone store, certificate store, the mobile application will not trust it by default. You can circumvent this. We do it in penetration testing. There's actually a documented way on how to do it. It's not too complex. You just add your user-added certificate authority into a resource section of the application, but you have to recompile it and you have to deploy it again on the mobile device. So we can see that vendors are doing something here. They're trying to push more security onto the network layer as well. Okay, so now we have some kind of a background of what we need to worry about. Data at rest, how do we store the secret, how do we protect the user's PIN, and data in transit. What happens with the data when it's flow over the internet or all kind of insecure networks. So let's take a look at the most common vulnerabilities that we found in last 4 or 5 years in those 30 plus applications. Let's try to map them to OWASP top 10 mobile vulnerabilities, because I know that there are a lot of OWASP guys here, so they like when I'm putting OWASP on those slides as well. The table that we have is not completely the same as OWASP top 10. For us, actually, server-side issues are something that we found most commonly. And unfortunately, those can be the most devastating ones. After that, we do have some insecure data storage, and I'd be happy to say that most, or maybe even all applications we tested have proper protection of data in transit. So they do good use of encryption to protect the data while it's being sent over the internet. So let's take a look at some examples. Worst case scenario, we have a mobile application which uses very, very strong encryption. Takes your PIN, encrypts it, and stores it locally. Or great, we have fantastic encryption algorithm, but the problem is that the key for that must be stored somewhere, right? If you just store the user's PIN encrypted on the device, how do we encrypt it? The key must be hard-coded in the application. Very bad. Some might say, let's hash it. Okay, that way we cannot reverse it. Good or not? No. How long is the PIN? 4 digits? 6 digits? How long does it take me to brute force to that on the most horrible hashing function? Doesn't matter, it won't be too long. So we cannot use that simple mechanism to store the data. Another reason for not using that is that most of the people, unfortunately, still do not use PIN codes. Check your friends, check your families, hopefully you do some security influencing on them, so you're trying to push them to use PIN codes on their mobile phones. Unfortunately, probably like 40% of people don't use PINs at all. There was an interesting research by this guy here who was looking at these Android lock patterns, ALPs, and he actually found out by analyzing thousands of ALPs, he found that 44% of them start in the upper left corner. It's just something that people typically use. And these here are top 6. That's top 6 ALPs that people use to unlock Android phones. If you have Android, I hope that yours is not here. Or if it is, you can say that you have a very secure ALP because it's in top 6. Not. So the thing here is that we cannot really rely on the fact that users will protect their phones. We have to do something else here. Remember the story from the beginning? We need to store some kind of a random secret which will be used as input for the Okra algorithm. So let's say it will be time-based, as our banks here typically use. So in that activation process, we have some random secret which should be generated by the device, sent to the bank, and now the bank and the device know the random secret. Okay? Random secret plus time is all we need to authenticate to the bank. The question is, how do we store the random secret? How do we protect it, right? It will be like a 20-byte random string. How do we protect that? Of course, the answer is, let's encrypt it, right? Because we know that encryption is impenetrable and best thing in the world. Good way, good thinking. But the question again is, how do we protect the key? So the key to decrypt that random 20 bytes, how do we protect that? Anyone with any ideas? Not you, Luca. Anyone want to throw any ideas? You know how to protect it? Okay, good, encrypted. let's see actually how we can do that. So basically what we want to do here is we want to use some kind of encryption algorithm which will always return some decrypted bytes no matter what PIN we enter. So if you enter good PIN, we get back good 20 bytes. If you enter a bad PIN, we get back another 20 bytes, which look completely random, but the attacker cannot know that he entered the bad PIN. The only way to verify it is to actually calculate the one-time password and send it to the bank. So that's the only way. He cannot do offline brute forcing. Why? Because every PIN will produce 20 bytes of something, and there is absolutely no way for him to know if those 20 bytes are okay or not. Now this is the main thing when we try to protect such applications. So the only thing that the attacker actually can do is send the OTP to the bank, and typically, at least with our banks in Croatia, he has 3 tries. So the third time it's incorrect, the bank will lock the account. So there are only 3 tries for that user to actually test it. And that's pretty good. Why? Because it's same as the physical token we had. The physical token we had, basically, depending on the PIN, gives us 3 tries, which means that if we steal that physical token, we have 3 tries. After 3 incorrect attempts, the physical token locks itself. Here, the bank locks the user's account. the mobile phone from that point is useless, unless you unlock it, and typically for the unlocking process, you have to reactivate or regenerate that secret again. So everyone got this, right? We stored 20 bytes, doesn't matter how many, and we want to have any pin which will decrypt something back, right? So we prevent offline attacks for a user. So what bad cases did we see here? Here are a couple of examples. So the first one I already mentioned. You know, they use 256 bytes AES. Oh, it's the best security encryption algorithm in the world. That's really bad. You hard-coded the key in the application. You don't do that. The other guy said, oh, you know what? I store PIN very, very securely. I use PBKDF2, so that's password-based key derivation function, very slow hashing-like function. You can see that they use counter of 1 million times, which makes it really slow. And he says, oh, you know what? On the latest iPhone, it takes like 3 seconds to calculate this. So it's very slow, you know. I'm trying to slow down the attackers. Not good again. How many combinations do I have with a 4-digit PIN? 10,000. Even if it's 3 seconds, it will be 30,000 seconds. Who cares? I can maybe run through all that. So we must not store anything which might show the attacker that he gets something right. Again, I'm coming back to the original idea. We take those 20 bytes and we allow any pin to decrypt them. Now the problem here is that besides those 20 bytes, if we add anything else into the same encrypted structure, this means that the attacker might decrypt something. He gets 20 bytes which are random. Okay, he cannot know if that's okay or not. But what if our developer decided to concatenate a username? For example, he said, I'm going to protect the username as well. I will encrypt that as well. That's very, very bad. Why? Because now when we use a bad pin, we get 20 bytes of random garbage, and we get some other garbage behind it. If we know there is a structure here, then that allows us to brute force the stored secret. And that's actually a bad way to store it. So what's the status in Croatia? Now that you know the vulnerability here, I'm happy to say that overall we have very, very good implementations. So while there has been some minor vulnerabilities that we identified previously, more or less the status here is okay. So most of the banks actually store this exactly as I described. They take some random content, encrypt it with the PIN, use the PIN to decrypt only and solely that random content, and that does not allow an attacker to run offline attack. And this is actually very, very good. That's something that we want to be happening in the future as well. We also saw some bad cases when they accidentally introduced some structural points, and that allows us to actually deduce if the decrypted content is okay or not. It doesn't even have to be that we understand all of the content. As long as there is some structure and we can know if it's good or bad, that's good enough for us. Because 4 pins, 6 pins, we brute force that in a matter of seconds today. The other thing that we see a lot, obviously, and which is good, although security through obscurity is generally not good, but it's not too bad here, is that applications get obfuscated. Now this is something that we normally recommend. Obviously, you won't do anything to secure your application with this. You will just make the analysis process much more complex and time-consuming, which is okay. But keep in mind, sometimes people tell me, oh, but we obfuscate our application, and for your penetration test, we gave you an unobfuscated version. So are we secure? No. Then they tell me, how long will it take you to break this one? I don't know. Could be months, could be years. But once you deploy the application, it will be there forever, right? Until the next release. So you cannot rely on the fact that this will hide something. You can see here ProGuard, which is the default obfuscation package in Android development. On the left side, you can see the obfuscated classes. And they look really ugly, right? Difficult to read. On the right, you can see right-click in this program here, JDEX, which is something we typically use to decompile Android applications. So all I did here was right-click and clicked on the magic button which says unobfuscate. And this is what it did here. It didn't really unobfuscate it, but this is much easier to read. So I can much easier, analyze such an application. What's the status with our applications in Croatia? Good. Absolutely every application that we tested that came from the store actually used at least ProGuard obfuscation. For those who maybe want a little bit more security, there are some commercial packages such as DexGuard, which can take this obfuscation to the next level, and it makes really complex job for a person who is attacking that or analyzing that application. Keep in mind, if you're doing a penetration test, maybe some of you are for other companies as well, I always tend to ask to get unobfuscated version. Why? Because we know that any obfuscation can be circumvented. It's just a matter of time. And you don't want people working on this to waste 4 weeks on cracking obfuscation, and after that actually using 1 week to find vulnerabilities in your application. So that's something you want to evade. Now, bugs in code happen quite often. I would normally say, unless you've seen this presentation before or in this particular slide, who can tell me what the problem here is? Okay, you be quiet. You saw that before. You look at it. So someone who didn't see this or pretended you haven't seen this, can you maybe identify the issue here? And this was a huge issue. Why? Because it happened, we found this after the application was deployed. When it's already deployed, everyone has it on their mobile phones. Okay, since I don't have a lot of time, I'll tell you what the problem is. And it's not base 64. People see here base 64 and say, oh, base 64 is bad. It's not base 64. What happens here is that the developer first creates a key, which is created automatically. This is good, totally random key, everything by the book, all fine. Then in the next line, he wants to create an initialization vector, IV. But check what the problem is. He used the wrong variable. So instead of assigning this to IV here, which is something that he wanted to pass to the function here, IV64, he actually overwrites the key. And every single application in the world has the same static key, which is this base 64 encoded. Very bad thing, very tricky to spot, and this is just a typical developer mistake that can sometimes happen. Again, our applications are relatively good, obviously, thanks to all the vulnerabilities we found that they fixed. But bugs in code will happen inevitably. We will miss them, developers will miss them, so it will always actually, it cannot be unfortunately avoided. The good advice is I think that any parts of the code which actually do some sensitive crypto-related things should be double, triple, quadruple checked, because you don't have to double check the whole application, but something which is working with encryption should be actually double checked. Here's another one. For people who know Android, maybe you've seen Android manifest files. Android manifest files basically define permissions that the application wants. So once you install it, that pop-up comes and says, this application wants to be able to talk to the internet, wants to be able to do this and that. This is defined in an Android manifest file, which comes with the application. In the file, you can define so-called intents. You can see one here. And then you can say who can call this intent. That's like an action in the application. So here, we have an intent which is called pin change. I think we can all understand what it does, right? Unfortunately, they opened it to the whole world being your mobile phone. What does this mean? This means that another application on your mobile phone can actually call this function and change your PIN, because the developer incorrectly wrote permissions in the manifest file. Or we can do simply this. This is just AM command. We start this, and basically on the screen, you have a window that pops up and says, okay, let's change the PIN. So we completely circumvented the part which says enter the old PIN first, right? We came to the screen which allows us to change the PIN. There are other bad things in this application, but this is one of the examples that we managed to find. And again, this was by a huge software security vendor. It wasn't a Croatian company. It was a world-known company. And when we got this to a penetration test, I said, it's like a world-known company. What will we do here? It's, I'm sure that thousands of penetration testers check this, and it turns out that they actually didn't. In Croatia, yay, all 100% tested applications had good permissions and Android manifest files. We did find some security vulnerabilities in libraries by other security vendors, which means even though someone big might come, to your bank or organizations, don't blindly trust them. doesn't mean that they're doing all things correctly. And actually, it's amazing how many times we have to explain some of the security things to the big vendors. They simply don't get it. The company is too big and it gets too watered down. So, a couple of slides and 5 minutes left and I'll be just on time, I think. Right? Yes, cool. All right, some client-side attacks. These are actually very rare. They don't happen all that often, but sometimes we do see interesting vulnerabilities which you actually wouldn't expect. So if someone told you that you can have a cross-site scripting on your mobile phone application, typically you would say like, what? It's mobile application. How can I have cross-site scripting on mobile application? Well, unfortunately you can. Why? Because not all mobile applications are what they pretend to be. Sometimes they're actually browsers which are in no window frames that you as a user cannot actually easily see that this is not a native application. That's actually a browser shell, and the application uses HTML, JavaScript, CSS, whatever, connects to the server, and then displays the data. And on your phone, it looks like any other application. It doesn't look like a browser. Those applications obviously are vulnerable to any other security vulnerabilities that are meant for browsers. I'm pretty sure that Miro will have a good presentation tomorrow about cross-site scripting, so we'll see what we can have in mobile applications as well. So this was one example of such an application. We were testing internet banking application, and we had two channels, mobile and standard web-based internet browsing, internet banking application. And the funny thing was that the browser-based interface was completely secure. We were not able to do anything. So we put some cross-site scripting. It was correctly encoded when being displayed back to us. But when you went to the same web page, which you don't see really, with your mobile application, you just click on one window and you go there, that embedded code comes back and gets executed on the mobile phone. And with this you can do bad things. Which bad things? Well, whatever permissions the mobile application has asked for, we can actually run through this. If the mobile application has asked for a camera, we can, in theory, enable camera. Why would mobile banking application ask for camera? Barcode scanning, QR code scanning. So all of them say, I need camera access. Sure, there you go. I'll give it. I want to do it. That's the best feature. I love that feature. So basically, it can use the camera, right? So anything it can use, we can use from this interface. Okay, so just for last couple of slides, data in transit. Again, as I said, almost all tested applications use SSL, which is really good. One of the recommendations here is normally to do some kind of certificate pinning. We started seeing that developers started using certificate pinning. There are some, let's say, weird implementations, maybe don't kill me, by some of the vendors which are present here as well, so I must not name them. So they use some kind of like SSL simulation, let's call it that way, which works okay. Maybe the problem with that particular approach is that if something happens to or some new vulnerability gets published for that algorithm or encryption algorithm, then that particular vendor has to fix it. If you use the OS provided libraries, I'm pretty sure that like Apple will fix it before. But this is generally okay. And the worst thing ever, server-side attacks. Now it looks, unfortunately, as we got back to year 2000, so some of the vulnerabilities that I never saw before, like we always in the company, we always have a joke, have you tried doing negative transactions? Like transferring minus 100 euros to another account. And the joke is typically, yeah, that never works. And actually, I don't remember that it ever worked until mobile applications came back. And for some reason, developers again consider them to be completely closed environments. No one can change anything. No one can change my parameters. I can trust everything that comes from the mobile device and then just leave their system wide open. We saw all sorts of scary bugs here. And I mean really, really scary. So they range from like silly information leaking vulnerabilities, nothing very bad, to high-risk direct object reference vulnerabilities. Sure, I have a window where I can download my statements list from my bank. I change the number, I get someone else's statement list from the bank. That's pretty bad. But for the developer, he doesn't know how you can change it. It's not that straightforward to intercept the traffic from the mobile device, but it's not too complex either. We can do it relatively easily. And this is the best or the worst, depending from which point of view. For us doing the test, it's always the best. For the developers, not so much. Some critical privilege escalation. What kind of privilege escalation? Well, maybe the application at one point, after I authenticate properly, I get some data back from the server, the application sends it back, and that data is my ID number, user ID number. What happens if I change that? Oh, look, I get someone else's account. Full, total control. Why did it, maybe you ask, why did this happen in the first time? Maybe, this guy is just telling us jokes here, that can never exist. It can, because in complex environments that we have now, so we have all those different digital channels, when you add mobile applications and you want to make them work as quick as possible, quite often there are weird interfaces between different components in the system. And maybe the different developers build those components. And their expectation is, okay, the other guy implemented security controls. And this one says, oh, the other guy will check this for sure. You know how it ends up, no one checks what's going in. And unfortunately, this category is most common and can be most critical. So, I guess there will probably be more to come. We'll see how the future will develop here. There is obviously some, movement forward, and I said, especially with all those SSL, TLS vulnerabilities in the last couple of years, a lot of organizations are paying attention to network traffic, and I can see that it's actually getting much better, but I'm pretty sure that we'll have our hands busy for quite some time in the future. I think Ivica agrees with me. Okay, so thanks everyone. Thanks to the guy who made me speak in English. And yeah, if you have any questions, I'm here now, later, whenever.
Yeah, due to the time, I will accept one question. So if there's anyone with one question, go for it. Sure. Can you please use the mic because of the recordings?
Okay, my question regards the client side basically. So on the mobile phone, the bank I was previously in, the application, once you exit from it and leave your phone and someone takes it, they can log back into the application without typing the PIN, simply because it's in the memory and it's always active.
Yeah.
I see you didn't mention that, but...
Yeah, that's actually one of the good points. So typically, on the phone, when you click on the button, you just put the application in the background, you don't really log out. So it's something that we give to, businesses to decide. Do you really want to log out your users every time they click on this button? And most of the banks actually say, no, leave them logged in, but maybe put some kind of a timeout on the session. So if there is no traffic from the user for like 3 minutes, right, then kill his session. And typically it will be a very short time interval, maybe 60 seconds, 3 minutes, not more than 5 minutes. And with new applications, I saw that some banks here in Croatia use it, and I actually really like the feature. So, like on iPhone, when you click on the button, and when you scroll through the applications, do you know how it works? It actually makes screenshots of applications, right? Of every window you have here, when you put it in the background, iPhone creates a screenshot of that application, and it stores it on the phone. So when you double click on the button and you want to scroll to the applications, you see all those nice open windows. They're actually screenshots, right? And what can be on the screenshot? You can have critical information on the screenshot. Okay, you won't have a PIN, but maybe some big transaction that you made to someone that you don't want anyone to see. So I saw that some banks here in Croatia actually use the feature that iOS provides, which will blur that screenshot. So you actually can't see what it is. But in most of the cases, yeah, it will be like 60 to 3 minutes timeout for that feature. And that's a good point. That's a good point. Something people should be aware of. That when you just click this button, you didn't really log out. It's still alive. So thanks for the question.
Thank you. I just don't know why we are using the banks all the time as an example. I mean, you can look at my bank account, but my Tinder account, I don't know about that.
Well, fair enough. I
had to put a joke on me for once today.
That's okay. I used banks because most of the penetration tests we actually did are for financial industry. So that's probably like 95%. and they're more sensitive. So
Thank you again.
that's it. Thanks, guys.